Good afternoon, everyone, and welcome back to our Australian Geometric PDE seminar series. We're going to continue with our discussion of mean curvature flow with a view towards doing mean curvature flow with surgery. Today, I'm pleased to introduce you Devesh Rajpal from the Chennai Mathematical Institute, who's going to lead our discussion today. He'll be talking about asymptotic convexity in mean curvature flow. Thank you, Devesh.
Thanks, Tim, for the introduction, and thank you, organizers, for giving me this opportunity. So the theme of today's talk is asymptotic convexity in mean curvature flow. And the plan over two talks is the following. First, I'll discuss convexity. And previously, we saw Huiskin's theorem on convex hypersurfaces and how there's a nice convergence theorem from a general convex hypersurfaces to a round sphere in under rescaled mean curvature flow. But also, as was mentioned in previous talks, that there might be a singularity appearing if our surface is not uniformly convex, like neck pin singularity. But we'll see what we can say about a general mean convex hypersurface flowing under mean curvature flow. And so there's a limiting argument based, and we can achieve convexity in some sort of limit, which is called asymptotic convexity. We'll see that. And to do that, we need, we'll also explore maximum principle in the mean convex setting, which was helpful, like we saw in the previous talks as well. And the crux of the proof lies on the following steps. The LPS, so the maximum principle fails here and doesn't give us much, but there's a way to do things, which is using integral estimates. So we'll do LP estimates, and there's a method called Stampaki iteration, which then gives us the desired result. The crux of the proof lies on the last two steps, the LP estimates and the Stampaki iteration. This is where the most of the calculation goes. And in particular, LP estimates require a lot of efforts. Okay, so continuing, the notion of convexity. We'll say a hypersurface is uniformly convex if a second fundamental form is strictly positive everywhere. This is equivalent to asking that the eigenvalues of the second fundamental form, which are called principal curvatures, are strictly positive, which will denote by kappa 1 till kappa n.
Devesh, can I ask you a technical question? Is it possible to make your PDF full screen? I see it sort of horizontally, and
okay.
I mean, if it's not, it's not. But
let me try. One second. Is this better?
Yes, much better. Thank you.
That's better. Yeah.
Okay.
That's better.
Okay, so as I was saying, a hypersurface is uniformly convex if a second fundamental form is strictly positive, and this is equivalent to asking that principal curvatures are strictly positive. And we saw a very nice convergence theorem for uniformly convex hypersurfaces last talk. But we can relax the condition a little bit and say a hypersurface is mean convex if the mean curvature satisfies. If the mean curvature is positive, which is asking that the trace of the second fundamental form is positive. And we want to analyze hypersurfaces in more and more relaxed condition in order to understand mean curvature flow. And this will be a starting point then. So yeah, moving on. I'll need this definition of elementary symmetric polynomial. I'll set up, the notation is for us will be S subscript K for K products of vectors, say lambda I1, lambda I2 till lambda Ik, summed over different indices. So this is denoted by Sk and is called the kth elementary symmetric polynomial. And the reason to do this is that since we can't directly know the values of kappa i's individually, we approach the convexity using these elementary symmetric polynomials. Okay. So associated to each k ranging from 1 to n, we can define the domain of positivity of the first k symmetric polynomials, which will denote by gamma k. So gamma k for us will be all the vectors in Rn, such that S1 of lambda is positive and going on till Sk of lambda is positive. Now, notice that gamma k forms cones in Euclidean space. If I multiply, if x is in gamma k, and if I multiply it by a positive scalar multiple, positive scalar, that multiple will also be in gamma k. So these are cones in Euclidean space and also satisfy inclusion property, since I'm adding more constraint if I increasingly. So gamma n will be the smallest subset included in gamma n minus 1 going on till gamma 1. And in this formulation, our hypersurface is mean convex if the vector, the mean curvature vector, which will denote by kappa 1 till kappa n, is in gamma 1. Second. Yeah, so now I'll require a lemma from convex geometry, which says the following. Let A be the positive quadrant or the positive cone where all my coordinates are positive. Then the set gamma k will coincide with the connected component of the positivity of just Sk, which contains the positive cone, the positive quadrant. And the takeaway from this lemma is that the cone gamma n coincides with the positive cone k. So asking a vector to be in gamma n is same as saying all its components are positive. So kappa 1 greater than 0 till kappa n greater than 0 is equivalent to saying that kappa 1 till kappa n is in gamma n. So for us, this will imply that a uniform convexity of a hypersurface is equivalent to asking if the principal curvature vector is in gamma n. So this sort of establishes a hierarchy of convexity where gamma 1 is the least in some sense and gamma n is the strongest convexity in some sense. We have explored mean curvature flow in gamma n, and we'll try to relax the condition and see what can happen. Okay, so moving on. The main theorem of this talk will be the following. Let X be a smooth solution of the mean curvature flow with n greater than equal to 2, such that our initial hypersurface is compact and of positive mean curvature. Then for any eta, there exists a constant depending only on the initial hypersurface and eta, c eta, such that the following inequality holds. Sk will be greater than equal to minus eta times h raised to k minus c eta k. And this inequality is trivial for k equals to 1, so we don't bother with that. But for higher case, it means that the symmetric polynomial of the principal curvature vector is the negative part of the Sk cannot grow faster than h raised to k. It will be within a limit of c eta comma k. And we'll see the consequences of this inequality soon and how it can be related to asymptotic convexity. So heuristically, we want to do the following. So given this inequality, we want to divide it by hk, but we don't mean the function hk will pick a maximum of hk over a compact interval, and will keep the compact interval limiting to 0, t. So, and now we want to divide this inequality by hk. Notice hk will remain positive because we are in a mean convex setting and it's a non-decreasing function. So we can divide, and sk divided by h raised to k is greater than equal to minus eta minus c eta k divided by h raised to k. Now, as t tends to capital T, which is the limit, which is the maximal time interval for our solution, h raised to k will go on infinity. This is consequence of this was done in previous talks. And this implies that sk divided by h raised to k is greater than equal to -2 eta for t sufficiently large. And if we rescale the hypersurface nicely, this can be thought of as the sk of the rescaled hypersurfaces. So sk tilde will be greater than equal to -2 eta. And notice the crux of the theorem says that eta was arbitrary. So we can select a sequence and out of which a convergent subsequence where our sk's will be greater than equal to 0, which will imply convexity of the limiting hypersurface. And we'll do that for each k, and the previous results come in place here, that gamma n coincided with the positive cone. So this is a rough sketch, and I'll do this rigorously in the next talk. So first we'll restrict ourselves to the k equals to 2k's. The higher estimates can be done either using induction or different function, and I'll come to what the function means for me. Okay, so now our goal is restricted to this. For any given eta, we want to prove that there exists a constant c eta such that S2 is greater than or equals to minus eta times h square minus c eta. And the way to do this is to consider the following function. Let sigma be in 0, 2. Consider a function g sigma, eta, which goes from our hypersurface to real numbers. Defined by this, we take the quotient mod a square by h square subtracted by 1 plus eta, and also take a factor h sigma, which will be important later. And this evaluates to this. If we expand the norm of second fundamental form as the sum of the squares of the eigenvalues, and h is the sum of the eigenvalues, so h square will be summation kappa I square plus 2s2. We can rewrite our g as g sigma, eta will be minus 2s2 minus eta h square upon h raised to 2 minus sigma. And this function is important because a uniform bound on this function will imply our estimates. How to do that? So suppose mod g has bound, uniform bound capital K, then we'll multiply both sides by h raised to 2 minus sigma, and using the previous equality, we write this left hand side as minus 2s2 minus eta h square is less than or equals to k times h raised to 2 minus sigma. And so minus 2s2 will be less than or equals to k times h raised to 2 minus sigma plus eta h square. Now we'll apply Young's inequality to trade k times h raised to 2 minus sigma for a better power up to a constant. So minus 2s2 will be less than or equals to, after substituting this twice, eta h square plus a constant, which is same as the result we wanted. Yeah, so this function is important to us, and a uniform bound on this function will imply what we want. Okay, so the first thought in our mind should be, what's the time evolution equation of this function in hopes of some maximum principle? And through some computations, we can say that its equation is Laplacian of g plus some factor times nabla h dot product with nabla g minus some factor of g with nabla h square, and this strange term for now, which is the difference of nabla a times trace of nabla, which is h in our case, minus nabla trace of h tensored with a. And this will be an important term, and Okay, sorry. Moving on. And we'll also get a residual term plus sigma mod a square g sigma comma eta. Now notice that this term can be dealt with using maximum principle. These terms are in good sign, negative, if you want a uniform bound on G. This term is also in good sign, negative, but this will be a problem. We don't know how to handle this term. So we can't directly apply maximum principles. Because of the we can't apply maximum principle because of the presence of the last term. However, let's see what happens if this term is not present there, which is sigma is 0. And so when sigma is 0, our G is mod a square by its square minus 1 plus eta. Ignore that for now. Less than equals to some constant depending only on the initial hypersurface. Yeah, but I'll come to the point why we need sigma greater than equal to 0 for the asymptotic convexity estimates. And the reason is, if we let sigma equals to 0 here, we'll not have control over the coefficient of h square. These two will be the same, and we'll get the coefficient as k plus eta. And notice that in the previous some sort of asymptotic convexity, I really needed this arbitrariness of eta. So sigma equals to 0 will not do for us. However, it implies a nice result that mod a square by h square is bounded by independent of time. And together with algebraic identity, h square less than equals to n times a square. This implies, this is purely algebraic identity. This, when simplified, is sum of the differences squared. Yeah, so summation kappa I minus kappa j square, purely algebraic. So this in particular implies that h square by n is less than equals to a square, which is less than equals to, from the previous result, some constant times h square, constant independent of time. So this implies a nice result that for mean convex hypersurfaces, the blow-up rate of mod a square and h square is the same. And later we'll see that type 1 and type 2 singularities are defined as defined depending on the blow-up rate of mod a square. But because of this result, it's same as using the blow-up rate of h square. But this is strictly for mean convex hypersurface. And yeah, this will also imply a bound on G sigma with a multiple of h raised to sigma. So I'm using the same constant for now. We can take the maximum of these two constants. Sorry about that. Yeah, okay. So moving on, our direct attempt with maximum principle on uniform bound of G sigma did not achieve what we wanted, but there's a way around it. And our next hope is an integral estimate of G sigma comma eta. So let G sigma comma eta plus denote the positive part of G, and a uniform bound on G, same as asking a uniform bound on G plus from uniform upper bound. And so even though we couldn't achieve a uniform bound directly, we can achieve LP estimates for now, which is that for any eta in 0, 1, there exists constants A and B such that the LP norm of G, the positive part of G, is non-decreasing function if the following inequality holds, which is that our P is sufficiently large and sigma is sufficiently small in the order of P raised to negative half. We'll need constants for doing this, A and B. Okay, so let's try to get a hold on the time derivative of LP is LP norm, and it satisfies this inequality, which so there exists constant C2 comma C3 such that time derivative of this LP, time derivative of P power of G plus is less than equals to some constants of P square multiplied by nabla G square with good sign, negative sign. Again, a negative sign with nabla H square. That term will appear again with a good sign. However, our previous problem will still be present here, that the P sigma mod A square G plus raised to P mod A square. And but the trick here is that this can be absorbed for integral estimates, so we'll be fine. And yeah, and also here we'll need, it need not be true for all P, but it will be true for sufficiently large P's. So
Devesh, could I just interrupt and ask
Yes.
which term are you eventually hoping to absorb that last one into?
A combination of all the terms.
Oh, okay. Thanks.
Yeah, there's a chat saying it's a beautiful estimate, but yeah, it requires a lot of efforts.
It's a much maligned but beautiful estimate.
Okay. So there exists constant C2 comma C3. Yeah, so that the following inequality holds. But it will only hold for large enough P's. And so, okay, yeah, again, there's one bad term which can be absorbed using all the other good terms. And this is a manifestation of the previous bad term, just integrated this time. Okay, so moving on. Differentiating with respect to time and using the evolution equation for P greater than equal to 1 will also suffice. So a time derivative of the P power of MT will have two parts. One, the time derivative of our function, the integrand, and the time derivative of d mu, since our hypersurfaces are varying as well. And it can be calculated that the time derivative of volume form is negative h square using some evolution equations. So yeah, so this is less than, and using our previous expression of time derivative of delta of G will get the following result. So there's a gradient, there's a Laplacian term, there's an inner product of nabla G with nabla H, there's nabla H square, there's this some difference term squared, and the last term. We are ignoring minus H square G plus term for now, and we'll ignore this term as well later. And in fact, we'll improve this term with we'll improve this term in a little bit. So yeah, and now to evaluate the integral, we do the following. For the term, the first term with a power of P minus 1 with G and now Laplacian of G, we can use integration by parts or Green's identities to shift the one Laplacian into two gradients with a negative sign. And in particular, this is the expression we'll get: negative of P integral of nabla G raised to P minus 1 in a product with nabla G. And nabla G P minus 1 will be P minus 1 times G raised to P minus 2 nabla G. So we'll get a inner product square. Yeah, so okay, this has been handled, and now we have a good sign for this term. Moving on, we'll handle this term now. So for the next term, we need the following lemma. This is a lemma observed in Huiskin's first paper on convex hypersurfaces, and which says that if xt is a point in the space-time such that g of xt is equal to g of it's a g is positive at x comma t. So we have an expression like this, that mod a square is greater than or equals to 1 plus eta h square, and also less than or equal to c naught h square coming from the previous maximum principles. Then we can estimate this difference term in terms of eta square and with a factor of h square and nabla h square, and some dependence on n as well. And notice that we need a positive eta to do this. Otherwise, this. So okay, we needed a 1 plus eta expression in our g's in order to do this. Eta equals to 0 would not have yielded anything. Okay, so from this we can write that so take any constant c1 greater than equals to this, the inverse of this, or okay, take a constant c1 so that 1 by c1 is less than equals to this constant, and we estimate we multiply this inequality by g raised to p minus 1 with divided by h raised to 4 minus sigma, because that was what was present in the integral estimates. And so this in particular will be greater than equals to g raised to p minus 1 upon c1, because 1 by c1, because this term is greater than equal to 1 by c1. And so g raised to p minus 1 divided by c1 h raised to 2 minus sigma multiplied by nabla h square. So h raised to 4 minus sigma becomes h raised to 2 minus sigma, because there's a h square term. Okay, so we'll split this into two parts. One part, so this can be written as sum of half of this plus half of this. For this is half of this term, and for the other half, we use this inequality that g is bounded by some constant time h raised to sigma. So in particular, 1 is greater than equals to g divided by c naught h raised to sigma. So we trade for c naught and an h sigma to get a factor of g. Any questions so far?
Yeah, Devesh, I wondered if you could explain that lemma. Like, how is that lemma proven? It looks pretty difficult to me. I can't obviously see how to show that would be true.
I don't remember particularly well, but you take an orthonormal basis and do some computation. So it's a general, this can be thought of as for any given tensor, symmetric two tensor T, we are taking gradient of T multiplied by the trace of T minus gradient of the trace tensored with T. So it's a somewhat a special expression, but I don't know more the proof. I can't remember the proof.
So just so I'm clear, like this isn't true for arbitrary A and H. This is only true for A and H as given by mean curvatures, right?
Yes.
So the Codazzi identity is important here. So that's the extra symmetry.
Okay, yes.
But then any tensor satisfying Codazzi would satisfy this.
I see. Okay. Cool. Thanks.
Yeah, and I would like to know that this type of expression appears in Hamilton's paper on Ricci flow as well, a very similar expression, but A replaced by Ricci tensor, and it's crucial there as well. I don't know any deep reasons why it. Okay, so
I guess saying that it's true for Ricci flow is good enough for me.
okay, yeah, I see a very similar expression in Hamilton's paper as well. And okay, so it was needed to get into a good term. We could manipulate the evolution equation of G with to get a good term with a sign here. Okay, so yeah, so there were three components in the integral estimates. We have estimated gradient Laplacian of G so far. We have estimated this term, and we'll ignore this term for now because sigma will it's in good sign and we can do better than the coefficients currently. What is remaining is the inner product term. So yeah, okay, I assume this is okay. And here we are getting the, yeah. So for the inner product term, we'll let P be sufficiently high. My brackets are not appearing here. Maximum of the 2 or 1 plus 4 C0 C1. Notice that C0 and C1 were independent in time. So this is fine. And like we can take high enough P's and use Cauchy's square inequality to get this estimate. So we can ignore sigma for now and just say this is less than equals to 2p times g raised to p minus 1 by h times gradient nabla h with the product with nabla g. And so Cauchy's square is the first inequality. And now we are applying AMGM or Peter Paul inequality with coefficients this. So I'm trading g raised to p minus 1 for a gp and a g raised to p minus 2. And gradient, these norms appear as squares here with a factor of 2 C0 C1. So yeah, this is fine. This is just AMGM, arithmetic mean, geometric mean inequality. And notice that this term was estimated just previously. This is this term. So we can use this in our advantage to say that this g raised to p with gradient h divided by h square is less than equals to certain factors times the difference square term with an and minus nabla h square term with h raised to 2 minus sigma. There's some difference between these two. I would just like to remind that this is with factor p minus 1. This is with this is with power p minus 1. This is with power p, and there's a sigma here, which is how we traded a g with a sigma, h raised to sigma. So, okay, so using this previous inequality, we'll get a difference square term minus g raised to p minus 1 upon h raised to 2 minus sigma term with nabla h square. And so for this term, if we let p sufficiently high, we can include a factor of p minus 1 as well. This is where we are using this. So if in particular p is greater than equals to p minus 1 is greater than equals to 4 times C0 by C0 times C1. So we are using this here. This is less than equals to p minus 1 by 2. And this is crucial. P minus 1 by this term appeared in the Green's formula of Laplacian, but we are using it here with a factor half. So we can Okay, so putting this all together, we get this estimate. We have a factor of almost p square, with g raised to p minus 2 times nabla g square, the difference square term, g raised, this was coming from this. We have traded in a product with a positive sign of difference square with p, and this is appearing here. This is these three terms, 1, 2, and 3 are coming from the inner product estimate. Yeah, we'll get this with a plus sign p, the difference square term. These two are same terms, p raised to p minus 1 by 2 over an integral of g raised to p minus 2 nabla g square, with a difference, and this good term where my C3 is 1 by 2 C1. So there's a one good negative nabla h square term with h raised to 2 minus sigma in denominator. Yeah, this term. And these were the previous terms. So we have, and simplifying this will lead the desired inequality. So there's a negative 2p appearing here, there's a p appearing here, which will lead to negative p. This p minus 1 by p times p minus 1 by 2, with negative p times p minus 1, this will be traded to half, and so yeah, we'll get the desired estimate. This, putting this all together. Yeah, and this was achieved only for some p greater than equals to a constant independent of time. Yeah, okay. Repeating what I've said, we got three terms: Laplacian G term, inner product term, and a difference square term, which were estimated against each other in some sense to get the result. So our problem hasn't been solved. We still have a bad term, p raised to p multiplied by sigma integral of g raised to p times mod a square. And so we'll need one more estimate to do this. We can estimate the positive term in previous time derivative as follows. So the bad term times a constant can be estimated against the previous terms. So we have this g raised to p minus 2 multiplied by nabla g square, g raised to p minus 1 times nabla h square upon h raised to 2 minus sigma, and the difference square term. So if we can arrange our constants sigma and p such that this bad term is still less than these other three good terms, we can say that d by dt of the pth power of this is less than equals to 0. So for sufficiently large p, wait, I'll say this. I forgot to include I forgot to upgrade one slide. So, okay, recalling, the bad term can be estimated against the good term with some factors including p. And if we can manipulate our p's and sigma smartly, we can our time derivative of integral of g raised to p will be negative. In particular, that will imply that it's a non-decreasing function it's a non-decreasing function, so it has a uniform bound, which is it's just a time function for us. And yeah, so we have obtained an integral estimate. I'll do this part later. We have obtained an integral estimate, and then there's a technique called Stampacchia iteration, which says that for a good range of LP estimates, you can get a uniform bound as well. So yeah, that's all I've prepared for now.
Cool.
It felt a bit short.
Let's thank Devesh for his talk.
If you have any questions. Yeah.
Yes, please. Anyone who has any questions or comments for Devesh, please feel free to share now.
Shut up.
So I think you just said this, but there's a second part coming up next week or in 2 weeks.
Yes.
Because now you have the LP norm, I mean, being non-increasing, but then I don't see what to do with that. I guess this is the analytic magic that happens somehow with this iteration that you mentioned, right?
Are you intending to prove this lemma next week, or just are you going to?
Yeah, it's
yeah. Okay. Yeah.
This lemma is like squeezing water out of stone, but yeah, I can do it.
Yeah.
Yeah,
Okay.
These LP estimates were like the crux of the calculations in the Huisken-Sinisterari's paper.
Yeah.
And once we have an LP estimate, we know a method to get an L infinity estimate, which is the Stampacchia iteration.
Yeah, right. So from a PDE point of view, this dilemma here you should think of as something like a Poincare type inequality, right? So it bounds a zero order term in terms of gradient terms.
Yes.
And then when it's kind of standard, you know, the Stampacchia iteration is a kind of standard PDE technique related to Moser iteration, where you get from LP norms to sup norms. So in the PDE world, it's this kind of standard, but I think this is the first time it was used in this sort of context.
Oh, okay.
Yeah. Good. Thanks,
I've got a
Devesh.
question.
Good.
Oh, sorry. Who determines that G sigma ESA was the right thing to study, and why?
I also don't know. I saw it in like the first Huisken's paper. There it was needed for pinching estimates required for convergence of convex hypersurfaces.
Maybe that's a better proof team. Who knows, right? Maybe we can find the correct function and then write maximum principle. But
I'm just wondering if this thing is just God-given, so to speak. Someone just picked it up and said, "Oh yeah, let's start estimating this."
So this was the proof that Huisken and Sinisterari came up with, which is kind of nice, and it's a little bit motivated by what Huisken did in the convex case. For the asymptotic convexity, there are other ways you can do it. So you can place this argument here using these, or really from iterating over elementary symmetric functions. You can replace with you just have to find a suitable function on the exterior of the positive cone, which has some good concavity properties. And then you could apply your argument to that. And it's not easy to cook one up, but essentially what Huisken and Sinisterari is cook up a function with the right concavity properties.
Yeah, I guess that's always the trick, isn't it? Finding the right quantity. Yeah.
But no, it's not something you just pull out of the air, I don't think.
This wasn't needed in Ricci flow, for example. There, we could directly apply maximum principle on some complicated or sensitive estimates, but this iteration technique wasn't needed there.
That's right. That's right. Ricci flow, you get the pinching of the eigenvalues for free from maximum principle. Yes. And in a way, Huisken's paper was, he really did it by trying to emulate Hamilton's 3D Ricci flow paper. And this was
the natural.
So he had to come up with another way to do it.
It's the natural thing to try first, see what Hamilton did, and then try and do that. Yes. Finally, a silly remark, Devesh.
Yes.
I'm glad you pointed out there were brackets missing, because I saw the expression maximum of 1 or 2, and I thought, well, why would you write that? I know which of those two numbers is bigger, but yes, it brackets.
Yeah. Here, we mean.
Yes.
Got to use that backslash before the curly brace.
Yeah.
Right, any final comments? If not, then let's thank Devesh again for taking us through some somewhat complicated estimates.
I have a write-up present if needed, which expands on most of these calculations.
Yes,
Yeah.
Devesh has indicated that he'd be willing to share with us some of his notes. We'll aim to put them on the website eventually. And Devesh, was it next week? Are you hoping to speak next week, next Friday, or do it sometime else?
Is it fine if there's a 2-week break?
That's fine.
Okay, so then
Yes, I'd say that's fine. All right, cool. Looks like we'll take a break for a while, guys. Hope you enjoy a couple of weeks off. And thanks again for attending. I'll stop recording now.